All right, let's go ahead and get started. I know others will join us here shortly. I want to just remind everyone this event is going to be recorded. We will be sharing this as well on our YouTube channel and sending out to all participants and those that registered. There is a chat feature if you have any questions during the event that you would like to ask Dave and Keith. Please be sure to use the feature to ask those questions, and I'll try to monitor that. And if we don't get to them during the event, we will certainly get to them during the FAQ. This event we're talking about today is data acquisition, unlocking the power of DAQ. We've got a whole series of topics that Keith Skidmore and Dave Reardon will be covering for us. They bring a lot of experience and will be sharing their expertise and kind of real world applications. So what kind of topics will we be talking about today? We'll talk about some basics about data acquisition systems, how things have been evolving, the history of DAQ, trends that we're seeing in the marketplace. We'll detail a lot of the different products that can be used in different systems. We'll also show you how those come together in what we refer to as data AQ packs. We'll also make sure that we answer some questions about software considerations. It's an important component, obviously, when you're talking systems. We'll review some best practices and tips and show you some exact applications and use cases across a variety of different industries, and then get to those FAQs. Again, thanks for joining us, and I'm ready to hand it over to you, Dave and Keith.
Okay, so to start off with, data acquisition system basics. You go to the next slide. So the first thing that we need to do is define what is a data acquisition system. A data acquisition system consists of hardware and software components designed to collect, process, and analyze data from various sources, and then further convert that into a digital format for analysis and storage. Next slide. Let's see, so the different components, what makes up a data acquisition system? Obviously, the first thing you need to do is figure out what you want to record, the input. Those can be sensors such as force, torque, accelerometers, thermocouples, just about anything out there as far as sensors go. It could be digital signals such as digital I/O, counters, encoders, and such. You always have to have some type of timing signal, whether it is iRig time, GPS time, possibly system time from your computer, or some other source. And of course, an additional type of input can be a serial stream, such as RS-232, RS-422, maybe a PCM stream, or some other type of serial stream. The input gets connected to some type of signal conditioning circuitry, which provides excitation to sensors. It has an amplifier, voltage offsets, filters, and such. The signal conditioning system also has A to D converters. Those A to D converters can be sigma delta, delta sigma, SAR, successive approximation register. All of these, some systems combine those and use multiple different types. The differences of these and why you would use one rather than the other would be a entirely different additional session unto itself, because there are many different components of that. D to A converters, a DAC, DAC that is, of course, not DAQ. This is used very often whenever you want to convert those digital signals back into an analog signal and output some type of voltage or current to drive some other component, such as an analog meter. The next component is your computer and the software. This is used for processing, analyzing, displaying, and recording the data. And then finally, there is that output signal, one of which was coming from that D to A converter. they can be, it can come in various different places within a system. For very low latency systems, it's very common for it to be come out directly, even prior to the A to D converter, directly from the signal conditioning circuitry. Or it can be from the DAQ, or even after processing and sending out a completely separate signal. Next slide. Different types of data acquisition systems, classifications and types. There are analog data acquisition systems, digital data acquisition systems, embedded DAQs, mixed signal DAQs, and application-specific DAQs. Next slide. For an analog data acquisition system, these are primarily used whenever there is some type of analog voltage signal that is coming in, whether that be from a sensor that measures load, force, torque, strain, temperature, pressure, voltage, acceleration, various other ones, and many other physical or electrical qualities. Next slide. For digital data acquisition systems, these are systems that are requiring digital signals, such as digital I/O, on-off states, counters, encoders, serial streams, any type of text data that might be input, video signals, GPS signals, and many, many others. Could be avionics buses. Lots of different types of signals are included within digital systems. Next slide. For embedded data acquisition systems, these are systems that are integrated into other devices or systems, such as embedded systems, Internet of Things devices, industrial control systems, and such. An example of these, I'm sure that everybody in this meeting has a cell phone on them. Your cell phone has an embedded data acquisition system in it. To process your the audio, you use it uses an audio DAQ, or there's other components that process things like a MEMS accelerometer and or a GPS system. For mixed signal data acquisition systems, these are a mixture of any of these different types that we were already discussing, such as the analog, digital, or embedded systems. And it could be additional systems included also, where you have within a single system, you might record sensors, avionics buses, digital I/O, or even some of these systems have embedded DAQs within the system itself to monitor things like temperature of the data acquisition systems or systems like that. Next slide. Evolving DAQ requirements within test and measurement. This timeline is broken down. I have it broken down just into 3 different areas. Each of these areas can be broken down into multiple other systems, but just to simplify it, I start out with historical. Next slide. These are systems that were pre-1980s. They were extremely large systems. You know, back in the 50s, they had it was something similar to what's shown in the picture here. It could take up a whole room just for the DAQ system. You know, as they move forward into the into pre-80s, you know, they had some of these systems on you might have seen on a rack of data acquisition equipment within an airplane. They were extremely large, took up a lot of room, very heavy. They used typically used a 14-track 1-inch tape that was that would only record maybe for an hour or two, depending on the how fast you were recording data. Very you know, back in when they first started using those 14 tracks, one sensor would be recorded on each track, and so it took up just a ton of room. It had very limited bandwidth. If you were recording something at 1,000 samples a second, that was very fast. They all had limited storage, as I mentioned, and there's also obviously very many other limitations. Next slide. So present day, I've kind of lumped into anything from the mid 80s on. And the reason why I started there is because in the mid 80s is whenever different companies started coming out with Windows-based systems, within your PC. So software started advancing a lot, and very often maybe it had just a board that was within your computer that recorded the different signals, or a system that was connected up directly to your PC for viewing the data. With this, we started to get a lot faster data, had higher bandwidth, started recording things at, hundreds of thousands of seconds, and even into the millions in the last 10 years or so. Storage space, the industry leveraged what was coming out of the PC industry to make it so that you could record just enormous amounts of data in a very short time. Just as an example, an aircraft like the F-35, they record terabytes of data in over a period of one flight that lasts a couple hours. In addition to that, we started using a lot of mixed signal data acquisition systems. Systems started to get very small. Real time was, instant gratification is what we were looking for here, and we were able to make it happen. In the last 20 years or so, they came out with a system that makes it a lot easier to program your system by using TEDS chips. You could this is to store information about a given sensor on a chip that is either within the connector or even on the sensor itself, to make it so that it identifies and programs the system as soon as you connect it up and start recording data. And then finally, we started making it so that you could add in very complex algorithms. For example, our 6-axis load cells that record force and torque in all 3 axes. We use very complex matrix math within our system, in turn 6 or even 12 inputs with some very complicated math going on to get out the 6 different outputs. Next slide. So some trends that have happened over the last 5 to 10 years in the industry. Satellite telemetry started coming around. This was very interesting because it made it so that a given test can be taking place here in the U.S., but somebody over in England could be monitoring the data real time by sending data up to satellite and then back down to wherever the viewer is. Internet of Things started tying in everything into a data acquisition system, making it so that things that are you could do things on your cell phone to tie into your system or other devices. Fiber made it so that you could record things much faster. As I mentioned, the F-35 recording all that data, they use fiber channels as an input into the system for a lot of that data. Wireless has been coming around over the last probably 15 years or so, but it started to really get really good in the last 5 years or so. We have many wireless devices that Keith will talk about a little bit later, but it makes it so that you are able to save a ton of weight from not having wire and cable stretched out within a given test article. For example, on the aircraft, whenever you're running hundreds of cables that are 100 feet long, that is a lot of weight, and weight is not what you want on a test aircraft. Wireless makes it so that you don't have to carry all that weight. In addition, there's some devices in the last few years that have come out that are inductively powering the sensors, such as our axial TQ torque device. It makes it so that very fast churning measurements, such as you see on motors or helicopter rotor blades or something similar to that, you can attach one of these devices and not have any cabling between the part that is rotating and the solid structure that is attached. Cloud-based storage is another big one that's been coming up over the last few years. Again, using cell phone networks, you're able to connect up a data acquisition system directly to a cell phone network and record data in a cloud storage place. That way you could view and monitor near real time anywhere in the world. See the embedded signals. I discussed that earlier. It's just about everything that we use in our lives has some type of embedded system. For example, a laptop computer, being able to monitor when as soon as the system knows whenever you lift up and open up the top, because there is something within the computer that is monitoring and seeing that you have opened up the top. And then finally, miniaturization of data acquisition system. Things are getting smaller and smaller, and it's really good in applications where space is limited. Being able to wear a device, for pilots or having. I've seen systems where, like for the NFL, in their mouthpieces they have systems within the mouthpieces even now. It really is amazing how small devices are getting. Next slide. So what is all this doing? The bottom line is we want more data, we want faster data, we want more accurate data, we want to make faster decisions, and we want to do all this now. And to top it all off, we want to be able to do it easier than we have in the past. Easier on the user, that is. For the companies that are building these systems, obviously it's a lot more work to make them that small. All right, I'm going to turn it back over to Keith.
So I'm going to talk a bit about interface DAQ products. So nice thing about interface products is the ones we offer are very specific to test and measurement and not super complicated. They're not super versatile in that it's not like these big systems you can buy from other companies that can do anything you want. These are catered more towards our end users who have a kind of a specific set of test and measurement requirements. So we have various different product categories. Blue DAQ is sort of our software package that's compatible with a number of our different hardware devices, and it's probably the most versatile of the software packages. And we're considering, what products to entertain or to consider. Some of that comes down to what software is capable of, and different products will have different software packages. WTS wireless system has its own software and kind of ecosystem of hardware. You can convert wireless signals into digital data that could be, connected into a system. Could also be logged and viewed on a PC using software that comes with the wireless system. So there are PC modules that convert wireless into data on the PC that can be logged, graphed, and stored. Some of the torque transducers have embedded USB amplifiers, so they have a USB connection to the PC. Also, RS-45 is available. That PC connection can be used, into somebody else's or their own software, or we do have software that comes with these systems that allows display and logging of data, calculates horsepower, for example, on a torque sensor. There are various PC interface modules which take sensor inputs and convert them into a connection to the PC, and they come in different numbers of channels, single channel up to 8 channels, and then they can be combined for any number of channels by adding multiple modules. Again, some of them are portable, handheld with batteries. Some of them will log to an SD card, so they're completely independent of a PC, and then you can read the data later. Moving on. So considering, which DAQ product makes sense, feature set is something to consider. What do you need it to do? Do you need it to do a whole bunch of different things? Do you need a lot of programmability, or do you need something that's kind of plug and play, you turn on and start measuring? Also, what kind of inputs are available? Do you have millivolts per volt, which would be a standard bridge sensor? Do you have voltage inputs, milliamps? Do you want strain gauge with bridge completion, maybe an encoder or linear or rotary encoders, pulse inputs, frequency, all those things are possible. Need to define what those may be. It's also interesting to think about if you're looking at a load cell, what else do you want to measure? Maybe we have a DAQ that could accommodate some of the other sensors you already have on hand. Form factor is going to be benchtop. Is it rack mount? Is it something that's very small, can be hidden inside something? Doesn't want to be portable, battery powered. It have to be rugged. You know, for example, if somebody were to be adding it to a system that might be seeing some impact or whatnot. Can sample rate. Some of the systems sample relatively slowly, you know, hundreds of hertz, you know, up to, you know, tens of thousands of samples per second. And it just kind of depends what's necessary. More isn't better if you don't need it. Typically, the data files get quite large when you have higher sample rates. So again, you don't need any more than what is necessary for the test. Connectivity, can you connect to a PC over USB? Do you want something like EtherCAT or TCP/IP connection? Are you going to connect to your own software, or do you want to use software that's included with the system? Power supply, you know, do you have you know, wall power, or does it have to have DC power? Is it going to be on a vehicle? It might have a specific, you know, 24 or 12 volts if it's on a car. Those are important to consider. You don't want to get stuck with something that can't be powered. And then again, channel count and dollars per channel. Some of these single channel and small channel count devices, very economical. They're not necessarily the best choice. So if tomorrow you have something else you want to do and now you don't have enough channels, so you might want to consider, you know, how many channels you need today, also what the expandability is, or what you might want to do down the road. Maybe you have some other tests you want to do that need more channels. Might make sense to go for it now as opposed to having to start over next time. Next slide, please. So starting with our kind of our biggest channel count DAQ would be our BX8. Comes in 8 channel modules. They can be combined. This shows a rack where you have 5 different units combined for 40 channels total. Each BX8 also has 2 extra channels, so it's really 10 channels. The 2 extra channels are encoder or pulse channels, and then the standard 8 channels could be strain gauge, millivolt per volt, voltage input, PT 1000 temperature sensors. You can also take thermocouples, and you can combine any number of those sensors in one device, and it's software selectable. These have analog outputs that are actively scaled. So sometimes people want a system that will, say, provide digital data for data collection, but also want output signals that drive a controller or into a feedback loop. These have actively scaled analog outputs. These also work well with our 6-axis sensors. They can do the matrix math internally and then actively scale analog outputs according to the calculations. Also, digital data to the PC. Works with our Blue DAQ software. This included, and those software is actually written in LabVIEW, and so it's very LabVIEW compatible if anybody has you know, their own LabVIEW requirements or software they want to connect to a BX8. Another thing, they can be, say, combined and synchronized together. They sample 48,000 samples per second synchronously on all 8 channels. If you have 16 channels, you combine 2 of these, you have a sync cable that connects them together and syncs all the input channels together. Why is synchronization important? Not so important for static measurements, but you have, say, rapidly changing measurements, and you want each measurement to sort of, you know, synchronize with the other measurements. It's very important. 6-axis sensor, you're measuring signals and doing math on those signals. Very important that the each, say, snapshot of the signals is done, capturing all the signals simultaneously. These also come with EtherCAT and TCP/IP options. So again, if you're connecting a bunch of these together, it may be desirable to use something like EtherCAT. Next slide, please. So the BSC4D is kind of the BX8's little brother. It has 4 channels. It can be either millivolts per volt, voltage input, or PT 1000 temperature sensors. It also does bridge completion, and that's built in. So depending how you wire things up, you have a single strain gauge or a half bridge connected with bridge completion. So this could be useful if you have, say, a load being applied to a test article, measuring that with a load cell, and then maybe have some strain gauges on the actual device. The BX8 does that as well with bridge completion. Moving on. This is a BX6, which is an interesting device. It's Bluetooth and SD, data logger. So it's a wireless connection to a PC, again, compatible with our DAQ software. It can do the 6-axis axis calculations internally and process the data and then store actual resolved data to the SD card or transmit it over Bluetooth to the PC. Both of those can be done simultaneously. So say you're logging data or measuring data with the PC. If you were to lose connection for some reason, it still is logging to the SD card. Also, you can say set this thing up and then disconnect it from the PC and just have your tests run, and then you can later collect the data off of the SD card. Up to 3,000 readings per second on single channel mode, or if you say have 6 axes and it's doing the matrix math and all that, you can get up to 500 readings per second. It has a 3.7 volt lithium ion battery with integrated charging, meaning it does the battery management internally. Next slide. So we also have a BSC2 and a BSC1. These are 2 and 1 channel devices. These are quite economical if you just want a couple channels. The channels can be millivolts per volts, a milliamp. You can also do some bridge completion with some of these devices. And next slide shows the BSC1, which is basically the single channel version of this. This one actually has an analog output too. So you can have, say, a digital connection to the PC and an analog output. Next slide. So this is a 9330, which is interesting because it's got an SD card and a rechargeable battery. Also, it can be powered off the USB connection to the PC. It also has an external power supply if you want to plug it in. So very versatile on its power. You can walk around, log data to the SD card, bring it back, plug it into the PC, and download the data into DAQ or into any other program you want. It can also just be hooked up to the PC and used to log data into DAQ. It has an analog output, which again can be useful for controlling or retransmitting the digital data via an analog signal. And it, like I said, it has a USB and an SD card, and you can actually read the SD card over the USB port, which is kind of useful. You don't have to have an extra SD card reader. Next slide, please. So this is our newest panel meter. It's a basic meter that's pretty easy to configure. It has real words when you're in the menus, which makes it easy to use. It has a USB port in the back that can be hooked up to our DAQ software for basic data logging. Somewhat limited in its frequency, so if you want really high speed, this isn't the item. But if you're just trying to take basic data, it's great. If you want a panel meter, again, mount it on a bench or on a little desktop stand, connect to a laptop or whatever, display and log data next to it. Next slide. Back up. Third. All right. The INF USB 3 is a PC interface module that goes in line with the load cell. It's a single channel device. Comes in a bunch of different versions. Millivolts per volt, voltage input 4 to 20, TTL for encoders. Comes with a little different software. It's not the DAQ software. It's a dedicated software for this product line. It does graphing and logging. Samples pretty fast, up to 5,000 samples per second. It has 16-bit resolution, and it's IP67. So when it's attached properly on the cable, it's weatherproof or weather resistant. Next slide. So this is a 4-channel version of the previous device. It can mix and match on the channels. They are hard configured those so that it has to be specified at time of order. Say 1 channel measures TTL, 1 millivolt per volt, 1 voltage, for example. Again, the software can display, graph, and log the data. Next slide. We also offer what we call DAQ packs, and certain customers would prefer to buy something that's, say, self-contained. We can even provide the computer. This is an example of a touch screen portable computer. It's in a little bit of a rubber ruggedized case, which is nice. All of the software is compatible with touchscreen, and this is one, say, using DAQ. So you showed DAQ just showing 6 displays. This is used with a 6-axis sensor here. You can also do it with a 3-axis sensor, which is shown in the picture. And Again, it's compatible with any of the devices listed here. Again, why would you want the computer included? Well, some people like to buy a single test and measurement system that they own. IT department doesn't own it necessarily. Call this a measurement device. It also allows you to have something that's say licensed and freely usable by yourself. Maybe you don't have to consult with anybody else if you're going to borrow it or share it or whatever. Just own your own device. It's nice if it comes with the actual PC and software. Next slide. So this is showing basically similar configuration, but using wireless. On the picture, you see a little USB device that basically plugs into the PC or laptop and takes wireless data. This software is showing the toolkit, but there's also software and toolkits used for configuration and setting up these devices. All can be used for logging and displaying, say, single devices. We also have something called Log 100 software, which is compatible with these same wireless devices, but can actually show 100 up to 100 devices simultaneously. So you could be displaying, up to 100 load cells or pressure sensors or position sensors or whatever you're connected to, all on the same page, could be logging them all. And again, we can provide it with a portable computer or laptop. Next slide. So this is the software that this goes with the embedded torque sensor products. So these are torque sensors that have USB amplifiers embedded. They connect the software. And if you have torque and angle and speed, and if you have torque and speed, you can calculate horsepower. So you can say, show RPM, torque, and horsepower. It draws graphs and logs the data to a CSV file. So self-contained system. Next slide. So this shows our DIG USB. This is a single channel PC module. This is probably the most economical single channel device we offer. Comes with its own software. This is a toolkit that's basically used for logging and displaying data. Next slide. This is a 9325. This is a very popular handheld display. It doesn't log data internally, but it does have a USB connection to software. It has a bunch of features and settings and things that are more easily accessed via the toolkit that comes with it, instead of using the menus on the device. And then it also logs and graphs. Next slide. All right. Well, we've talked about various different software packages. We're now going to show you a few of them. Next slide. So this is talking about, well, what do you have to consider? Say we have 3 different USB modules that use different kinds of software. Well, which one's the right one? Well, is it for displaying, or do you want to log primarily? What do you need available in the display? Do you want to be able to configure it, or are you okay with just whatever it is? Do you need math channels? Math channels could be super simple, like A plus B equals C. Channel 1 plus channel 2 equals the total. Or you could do derivatives, or say center of gravity calculations, or calculate force vectors with multi-axis sensors. So the sky's the limit, but you need to kind of understand what you need to do before we decide which package is appropriate. Again, data analysis. Some systems will log data, say, to CSV files, and then you have to open that up in some other software, maybe in Excel. If you want graphs, you can draw them in Excel. Something like the DAQ actually has a built-in file monitor, which means you can open the data files and look at the graphs in the software, which is nice because instead of having to create a graph in Excel, it just does it automatically. And then you can zoom in and look at peaks and valleys and things quite easily without having to mess around. Again, if you have a lot of data too, Excel doesn't necessarily like very large data files, whereas DAQ can easily handle them. DAQ has up to 40 channels. Again, how many channels do you need and what expandability do you want? DAQ is the widest range of hardware compatibility. So if you're going with interface system, probably sticking with something that's in the DAQ family might make sense if you want future expandability. A VS3 has up to 4 channels. You can't combine INF 3s or SI USB 4s, though, so you're basically stuck with that many channels into the software. You could run multiple instances of the software, but you can't combine multiple devices into the same software. So that's a consideration. Next slide, showing a picture of the Blue DAQ software has various different tabs. You've got individual graphs. You've got a combined graph, which shows all of the channels graphed simultaneously. You could decide if you want to graph, say, all the channels versus time, or if you want to graph one or more channels versus one of the other channels, like if you want to measure and display, say, force versus displacement. You can also just have displays like we show on the bottom there. This is with a 3-axis sensor showing X, Y, and Z. You can change the names of the channels. Here we change them obviously to the axis names. Say graphing capability has a built-in viewer, which is quite nice instead of trying to mess around with Excel. It also compatible though. You can definitely open and look at the data in Excel or email it around in Excel format. You can save and load various test configurations. So say you had a setup where you had 6 channels of load cells, that could be in configuration 1, that could be say with the BX8, and then you might have another system where you have a BX8 or maybe 2 BX8s, and that's a 12-channel system, and you've got set up for some LVDTs and some load cells and some pressure sensors. You can pull up that configuration and it remembers everything you set up the first time around. Selectable sample rates. You don't always want to run at max speed. So for example, if these things are, say it's capable of 50,000 samples per second, you may only want to run it 100 samples per second. You can set that in the software and it decimates down to 100 samples per second. The software also very nice to use with our 6-axis and multi-axis sensors. Allows you to manage the matrices, load them in and out of the BX8, and select multiple sensors stored internally in the BX8. And one thing to note, the BX8 runs on its own, so you can use the Blue DAQ to say set up the BX8, load the matrix, have the 6-axis sensor running, configure the analog output so that the analog outputs say are scaled and actively following the 6-axis measurements, and then you can just connect the PC and the BX8 will just sit there and run on its own, still running its analog outputs, say to a control system or something. There's a pro version. All these software packages are freely downloadable. The BX8 though, and the Blue DAQ does have a pro version of software which adds a few dollars, and that adds complicated math scripting for the math channels and also some specialized triggering functions, among other things. Next slide. So this shows the software that's compatible with the INF3 or the embedded torque sensors or the SI USB 4-channel device. It's a little different flavor, as you can see. It allows you to display, any number of the channels and graph them. The graphs are stored as JPEGs, not as data, and then the data is stored as a CSV file. And this one doesn't have a built-in file viewer, so you'd be looking at either the graphs as they're saved, or if you want to manipulate the data and graph it, you'd be looking at using Excel. Next slide. Some of the other software comes with these toolkits and kind of dedicated software for the individual hardware. The wireless uses something called Log 100, which I mentioned previously. On the left here, it shows a mapping function in that software. So you can actually throw a picture in and then lay displays over top of it. And this is for an airplane jacking application. The customer wanted to jack an airplane, and they do it manually. And they're basically got guys running these jacks, and got to be real careful so you don't accidentally apply way too much load at one point and like break the wing or punch a hole in it or whatever. And so basically these displays are set to actually turn color. So you got green, yellow, and red. And if they're within certain values, it'll be green or yellow or red, and then they can control the jacking and make sure that the aircraft is evenly lifted. The DIG USB has a toolkit. You can see it's fairly basic. It just shows the load, and then you can also show a graph and log the data. And on the right is another display showing the VS software, which works with the INF USB and the SI USB 4. Next slide. Back to Dave.
All right, so the next section is data acquisition system best practices. There's I think 5 or 6 tips here that we have just to try and assure that that you guys that people are getting exactly what they need from their DAQ system. Tip number 1 is to make sure that you're selecting the right system, of course. It's very crucial to choose the system that is compatible with your specific force measurement devices and applications. Things to consider are your sensor type, what the output of that sensor is, whether it's a millivolt per volt, a voltage, or maybe it's a current, a 4 to 20 milliamp sensor. Let's see, things like your measurement range, the accuracy, your resolution of the data, and the sampling rate, taking into consideration things like oversampling requirements. For example, if the frequency of your measurement is measurement of interest, I should say, is or frequency of interest is 1,000 hertz. You taking Nyquist into account, you probably want to be recording at some factor above that, whatever your requirements are. For many people, the standard used to be 5 times oversampling, but that slowly has changed to make it so that 2 or 3.5 times oversampling is good enough. I know that there are some applications where you have to do 10 times oversampling, where the data is very fast. And of course, finally, you need to take into consideration connectivity options. You might need a wireless system or a cabled system, depending on what your requirements are. And then, in addition, I always like to throw in the idea that your size and form factors are extremely important. You need to make sure that the system fits into the area that you're purchasing the system for. Next slide. Proper sensor installation and calibration. It's very important for you to follow a manufacturer's guidelines for installation of a particular sensor. For example, on our low profile load cells, you need to make sure that you have a very flat surface that the thing is mounted up against. If it's curved, you're not going to get a very accurate measurement. With most of our low profile load cells, we sell a base included as part of it to help ensure this. Let's see, the cabling and the wiring is extremely important. Again, this is reiterated, many times throughout the presentation. The size of the wires, the length of the wires, the longer the cable run is, typically you need to have a larger gauge wire to assure that you're not getting a lot of temperature drift within the system. Let's see, calibrations. Again, follow the manufacturer's guidelines for calibrations. With our load cells, we typically recommend once a year. However, if we know ahead of time, we could do things to bump that out to 2 times or once every 2 years, or in a lot of systems, maybe your requirements are going to require you to do it more often. I've seen situations where customers are required to do a calibration before and after every single test. Next slide. Signal conditioning and filtering. Signal conditioning and filtering techniques are essential for optimizing the quality of your data. Of course, as we've been discussing, signal conditioning involves your amplification, zeroing or offsets to your measurement. Filtering, as I mentioned earlier, if you want to use infinite impulse response or finite impulse response or anti-aliasing filtering, all this will help assure that you get the best possible signal. And just as a mention, the BX8 that Keith mentioned earlier does have all these filtering capabilities within it. Next slide. Data validation and analysis. Let's see. Make sure you implement the data validation techniques such as range checking, outlier detection, look for errors, data integrity checks, so that you can identify and correct those errors or anomalies. Analyze the acquired data using appropriate statistical techniques and data analysis techniques. Make sure that you have the best data possible so that you're making the most informed decisions possible. as I mentioned earlier, being able to make those decisions at a much faster and much faster than we have in the past. The tools are there. We just need to make sure that we're using them. Tip number 5, system maintenance and calibration. I can't stress enough how important system maintenance is. That could be something as simple as cleaning out a filter near a cooling fan to make sure that the system is not going to overheat from the filter being clogged. The regular maintenance is very important. Cleaning your sensors is very important. Calibrations, as I mentioned a couple slides ago, calibration, you need to follow this stuff to the manufacturer's guidelines to make sure that you're getting the most accurate and reliable data over time. Next slide. Keith and I are going to alternate here on some of these DAQ applications and use cases. So the let's see, for this first one, the first application, this is a syringe plunger force measurement. The customer was looking for a method to measure how much force is required to dispense liquid from a syringe, a medical device, obviously. So we supplied them with one of our SMT S-type load cells, coupled with our Model 9325 portable sensor display. It's a handheld device. And as they press, as the actuator presses down, it measures how much force is required to dispense all the liquid. The 9325 does have an output that can be connected up to a laptop computer for viewing and recording there also. Next slide.
This shows a fuel pump optimization application. It's showcasing a torque sensor that has embedded USB and the software that comes with that. So basically the sensor is able to measure torque and RPM, and software then can calculate horsepower and display that. And the intent was to kind of tweak the parameters of the fuel pump and measure how much power it takes to drive the fuel pump while optimizing fuel flow. And all that can be done basically with this torque sensor and the associated software. Next slide. Bike handlebar fatigue testing. A lot of our customers are doing structural fatigue testing on articles. Bicycle manufacturers do a lot of testing, believe it or not. And basically in this test, there are 2 actuators that push and pull the handlebars, simulating somebody's hands on the bars as the bike bounces up and down. And there are load cells in line with the actuators and LVDTs measuring position. And these are all 4 sensors going back to an SI-USB 4, which is 4 channels of display showing, position and force at each end. And the test can be ran using this software to collect the data. Next slide.
So this one is an interesting one. Again, within the medical industry, a prosthetic foot performance. The customer was looking for a method to be able to measure force in the X, Y, and Z axis as they mechanically move the foot in a walking motion. They wanted to measure exactly how much force was being applied in those axes. So Interface supplied them with one of our 3-axis load cells. Between the right in the ankle area, between where the leg socket and the prosthetic foot is attached, and then that was connected up to a BSC 4D bridge amplifier, which was then connected up to the PC interface. And as the mechanical device simulated walking, we recorded force in the X, Y, and Z axis.
This is a self-contained measurement system. Wireless load cells used to tether helicopters down as when they, land, basically. And if you pull too hard on the tethers, right, that's damaging. If they're not tight enough, that can be a problem too. And so the customer wanted a self-contained system that had displays wireless communication from the sensors back to the displays. Had to be rechargeable battery, had to run on various different power supplies, whether it was vehicle power or wall or shore power, and had extreme temperature requirements because in flight could be exposed to very cold temperatures, for example. And we provided this entire solution. Next slide.
So this is a system where a mooring system for container ships, out in one of the ports. The customer was looking to be able to measure how much was pulling force was being applied to the different nodes that are attached to the port, the bottom of the port in the ground there. So what we did for this was we supplied load shackles that are connected to the node, holding down in three different locations on each one of those nodes. And those load shackles were connected to a 9325-1 handheld display so that they can measure instantaneously as a ship is connecting up. They can measure that. And then for long-term recording, the 9325 was connected up to a PC for long-term monitoring and recording. Next. This is a material tensile tester. What the customer was looking for is they had materials that are plastic, steel, or woven fabric, and they had an actuator that would push down on that with a rod and they wanted to measure the tensile strength, the yield strength, and the yield stress as it pressed down. So for this, we supplied them with one of our 1200 series low profile load cells, and that was connected to one of our SI USB 4 interface modules, so that as it pressed down, you were able to record all three of those measurements. Different triggers were set up so that as it yielded, you were able to get the ultimate load as it yielded. Next slide.
So this is a robotic surgery force feedback application. A lot of these systems have sensors embedded in them for measuring, say, torque, force, displacement. Also, when the operator uses the system, there needs to be force feedback and haptic feedback into controls. So this would be using BX8, where you have data logging to a PC, also actively outputting the sensor signals via analog outputs back into the controller for force feedback. Next slide. Tire test. We have sensors that measure two axes. This happens to measure force and torque. Imagine applying torque to a tire as it's rotating on a surface and measuring, say, side forces as you're kind of pushing and pulling it across the surface laterally. And this could be connected to this SI USB 4, which would measure force and torque and display the results on the PC. Next slide.
This next application is for aircraft screwdriver fastening control. The customer was looking. They had a automatic one of these machines that automatically screws in screws to different places on the aircraft, and they wanted to be able to measure how much torque as they were turning, and simultaneously see exactly how much clamping force was, underneath that screw. So we had a load washer underneath the screw. So the system was set up. We supplied them with one of our T15 hex drive rotary torque transducers for the screwdriver, and then we used one of our load washer clamp and force load cells under the screw to measure how much force as it was screwing down. We had those attached to an SI USB 4 interface module connected to a PC to log, display, and graph the data. Next slide. So these are just some frequently asked questions that we seem to get from a lot of our customers. Obviously there are a lot more questions that we get, but these tend to be some frequently asked ones. What are the pitfalls of using a wireless system? The wireless system, you have to be very careful with the fact that if you have multiple channels going into one of these systems, they are not going to be synchronous. Each sensor is going to have different latencies. You cannot. It's not good for very fast data, and sensors that need to be synchronous.
Also, there are limitations to transmission distance, and if you have it in a cabinet trying to monitor something, and the signals may or may not be able to get out. But we do have things like repeaters and remote antennas and things to help that. Next one is data acquisition system always recommended for multi-axis sensors. Well, for our multi-axis sensors, we typically recommend our BSC4D for the 3-axis sensors and the BX8 for 6-axis sensors, and it greatly facilitates the use of the sensor, does the matrix math internally for the 6-axis sensors. That said, not necessarily. If somebody wanted to say just display data, you could have 6 displays or 3 displays with a 3-axis sensor. So it really depends on what the requirements are for the end result.
Another question we get often is why would you choose a DAQ system over just a simple indicator? Well, it's in this situation, an indicator is actually part of the system. Either way, you're going to have some type of data acquisition, signal conditioning going on prior to the point that it gets to the indicator. I guess a better way of asking this would be do you need real-time recording, or do you want to do it post-process? Do you need to be able to act on a value immediately? Obviously, if you have an indicator, reading whether it's a handheld indicator or an indicator mounted on the wall, or even just viewing it on a PC screen, if you need to be able to act on that, obviously you need to be able to see the data near real time. If you just want to record the data and do post-processing, then you just need something like our BX8 connected up to computer recording data.
Can a DAQ be too much for some test and measurement applications? Certainly. Sometimes you just need a display, and then a handheld or a benchtop display is all that's needed. If you want to log data, though, something that does data logging obviously is useful, so you don't have to write numbers down. Some of our sort of small channel count systems, though, are also very useful, where you don't need a full-blown data acquisition system. Just a simple plug-and-play device that hooks up to the computer, lets you log and view data. So, yes.
Let's see, can you mix measurement types within a single instrument? Absolutely, of course. That's where we were talking about mixed signal data acquisition systems. And then even in some of our smaller ones, items like like our 9840, you could record a load cell and a thermocouple, or maybe an LVDT. Obviously you need to be able to have the extra channels. With some of these devices, we need to know ahead of time, obviously, so that we can make sure the correct signal conditioning component is within the system. But with others, that's built into the system already to be able to handle that. Let's see, items like our BX8 and some of the BlueDAQ supported devices, they have digital I/O and load cell capabilities. So yes, absolutely.
Does cabling impact? Yes, it does. Long cable runs can add large errors if they're low-level millivolt per volt signals, like coming from load cells or strain gauges. Certain DAQs will have 6-wire sensing technology to measure the excitation. Some don't. Some of the inline modules are kind of hardwired to the sensor, so they're calibrated as a system. The cabling is not a factor unless somebody decides to cut the cable and change lengths or whatnot. So yes, cabling definitely needs to be considered. Shielding, proper grounding, all of that goes into a good measurement system.
If you have additional questions for Keith and Dave, be sure to use our chat feature. We had a couple come in while you guys were presenting. Marcus was asking about where to find the sync cable discussed on the BX8 application in the manual. And Keith, is that something in the manual, or is that something that you would get separately?
We have a separate manual which is available. It's pretty simple. There's digital IOs on these devices, and they can be set for master slave arrangements, and then you basically hook up the DIO on one to the DIO on another, and they clock the two systems together or multiple systems together via the same methodology.
Good to know. Jason asked about getting the presentation. Of course, this is going to be recorded. We'll be sending out the recording as well. It'll be posted on our website and our YouTube channel. However, if you like the actual presentation, we'll certainly get back to you, Jason. Marcus also wanted to know what format is the toolkit provided for the 9325?
Well, it's downloadable from our website. If that answers the question, it's a program that's installed on the PC.
Perfect. So all of the software that we have available is on the website under the support tab. You can find our toolkits, our manuals, our installation guides. Everything was there and available. But if you ever have questions, be sure to engage with our application engineers, our representatives and distributors in field. They can help you find what you need. And then, of course, any other information that you have that we haven't been able to cover in this specific application about comparison of different systems and devices, our team is ready to engage and help answer those questions for you. If they weren't answered here, be sure to drop us a line, contact us, give us a call. And again, we'll make sure that you get all the information that you need. I don't see any other questions. So as we've come to the close, I'll just remind everyone we're a trusted partner for force measurement. We work with I need a single load cell up to building complete and complex systems. Our custom solutions experts understand how things work in the field. They can work with you to ensure that all your requirements are met, and we can even build the spec. So be sure to contact us if you have any questions. We have a lot of different offerings, thousands of products, and some things work well together, and others we can help create the right solution for you. So we've been building stuff for 55 years. We know that there's a lot of options for you. So please be sure to let us know how we can specifically help. With that, I will say that concludes our presentation today. Thank you so much, Dave, Keith, for sharing all your expertise. I know you have a lot more that we could have spent a lot of time on, but this is a great starter for people that are looking to get familiar with data acquisition systems and the depth and breadth of our solutions. We appreciate everyone's time today. Thank you for joining us at Interface. And again, let us know if you have any questions. We're here to support your requirements. Have a good day, everyone.